Okay. So we have this equation, right? The most general equation that we have, right?
Professor, it kicked us out. What would you say? I'm sorry?
Oh, okay. So what happens to FT was your question, right? So
Yeah.
we have this equation. This is the centripetal, this is the force equation along the radial path, right? So to keep it in circular orbit over here, right, if we have an FT, we have to increase V, right? The minimal centripetal force that we can have is when FT is 0, right? We're trying to find the minimum V. V is related to the forces through this equation, right?
Okay.
You want to make V the smallest possible that it could be. So to make V the smallest possible, we don't change the chord length, we don't change R, we can't change M, right? The only thing that we could change in this equation is the tension force, right? To minimize this V. If we reduce the tension force to 0, this will make V the smallest it could possibly be. Correct?
Yeah, but wouldn't the ball fall then?
No, it doesn't. That's the whole thing, is that it doesn't fall. So right at this point where the tension is 0, but it doesn't fall out of this arc, that's the point that we want to find.
Oh, okay.
So it's right before it starts to fall down out of this arc, where it would fall something like this, and where there's no tension on the string. So it's floating, it's free floating at that point.
Okay,
It's like when you go over a loop in a roller coaster, right? At the very top, you feel weightless, correct?
Yeah.
For the most part.
Okay, makes sense.
You feel weightless. So you want to find this special condition where it continues along this motion, the circular motion, but there's no tension. And that's the minimum velocity that you can have, right? And in that case, ft is 0, but gravity has to satisfy this equality for circular motion, where the radial force is equal to, mv squared over r. So we're finding that special position. So now that we found it, let's figure out what forces. So let's say if this is the speed and it's kept constant throughout the whole thing, right? What is the tension in the cord when it's at the bottom? If at the top the speed is just enough so that there's no tension, what is the tension at the bottom? Right?
Wouldn't it be mg?
Well, let's figure that out, right? So assume that the speed stays the same throughout this whole problem, right? Or hold on, let me see if that's. Okay, yeah. So at the bottom, they're assuming that V2, so this is V. V2 over here is 2 times V. So assume that that when it reaches the bottom, it speeds up, and now that the speed, its tangential speed is 2 times as what it was at the top. Right. So what is Ft in this case? So let's write down the forces on it, right? At the bottom, right? This still stays in circular motion, so we'll assume that, right? So that means that we have the tension force. Which direction is the tension force at the bottom? Anybody? So at the bottom, the rope is holding it from flying away, right? So the tension force is radially inward, right? This is the tension force. What's the gravitational force? Which way is the gravitational force pointing on the ball at this point? Anybody? Downward. Right? So it always stays vertical. Now we have Ft minus Fg. And then this has to satisfy centripetal the relationship for circular motion. We have this, right? And we assume that it's 2v. So minus mg is equal to 2v squared. And then I'm going to bring mg over to the other side. Over r, and then we had our quantity that we had for v1. If you remember, v1 was the square root of gr, so we can plug that in. So this is g over r, and when we solve this, right, the r's cancel out, we're left with 5gm. Okay. So the tension force is about 5 times the force that you would normally feel due to gravity. Right. Now, let's do one more problem. All right. Let's talk about skidding along a curve and banking it. Problems, and we'll finish it up here today. I'm going to go over time a little bit. I'll minus this from the time that we had. So let's calculate it. So we had 2 hours and 30 minutes. And then we had another 50 minutes. And then we'll subtract whatever we do today. All right. So let's think about a very practical application to this. And one practical application to this is cars on a highway. Having banked highway curves. And what this allows for is it allows us to go faster around the curves. And we'll explicitly calculate why this is the case. So let's think of a car, right? We have our tires, we have our car, right? Now, when the car turns, let's say when the car goes around a circular track like this, right? When the car turns to go around, right, for it to stay along this path, it needs some kind of centripetal acceleration towards the inside, towards the center, right? Otherwise, it'll keep going along the straight line. What force, in this case, on flat ground, provides the centripetal acceleration? What would keep it along this path?
Friction, maybe?
What?
Friction?
Friction? Yes, that's correct. So it's the friction between the tires and the road that will provide the centripetal acceleration, right? It provides this FR. Or let me just write, the force of friction is equal to FR, right? Once you overcome the static coefficient of friction, you start to slide off the road, right? You start to drift, right, from this circular orbit, right? And then once it starts occurring, you enter the regime of kinetic friction, which lowers which lowers the overall friction even more. And then once you start sliding, you slide off the road, right? And you've seen it a lot in videos and stuff like that. So once you start sliding, it's harder to get your control back, right? Now, one way to handle this is to introduce a bank on the road. So this car is on this side, right? Now, let's say if we have a bank in the road, let's see what would happen. We have a certain angle, right, theta. We have our car on our road now. Okay. And we're rotating around like this. So imagine this car going around this circle. At this point, consider it coming towards us or something like that. And it's along this bank. So it's coming towards us. It's about to complete the circle and go back around into the page over here. All right. So now let's consider the forces on this. Where's gravity? Well, gravity's downwards always. Okay. Whereas the normal force, well, it's always normal to whatever surface you're on, right? And then let me simplify this diagram a little bit. Okay. And then we have this angle over here. This is our theta, right? Now we have this. Okay. Now, which direction would be our centripetal acceleration in this case? Where should our centripetal acceleration point? Remember which way should the centripetal acceleration point? Anybody? Should point inwards towards the center, right? And inwards towards the center is actually this way. So this is going to be the centripetal acceleration in this direction. I'll just label it as AR, right? So now let's consider what points contribute to the centripetal acceleration. So not only, and then we have friction. right? And here,
So wouldn't the AR be the friction, or
what?
wouldn't the AR be the friction?
No. AR is the centripetal acceleration. It doesn't just have to be the friction. So whatever force that's along this radial direction, right? And besides friction, what else do we have along this radial direction? Besides friction, we also have the normal force, right? Part of the normal force is now pointing in the radial direction. So we no longer just need friction, we could also use the normal force to satisfy the uniform circular motion, right? To satisfy this acceleration. Now, let's first figure out what angle do we need to keep this car traveling around at a speed v and a distance r from the center without relying anything on friction, We want this bank to be perfect so that instead of using any amount of friction, we can just use all of the normal force as our centripetal acceleration, right? In this case, right, we'll have to figure out the component along the AR direction. And for this problem, we want our coordinate system to not follow the inclined plane, but to follow gravity and our centripetal acceleration. Because our centripetal acceleration is in the horizontal direction, that's what we're looking for. So we want to keep our coordinate system like this. Right? We don't want to follow the coordinate system along the inclined plane. Right? So FR in this case is what? MV over R. And this is equal to, if we look at this, we'll fully write it out. Right? So AR is equal to the sine of the normal vector because we're working with the opposite. We're working it with this in this direction, right? And then just for completeness sake, we'll use friction as well. It would be the friction, right? And then this would be and friction. So this is our coordinate system. Friction's pointing downwards like this, right? So that means that the friction is downwards like that, and this is X and Y. That implies that this is our theta now. No, I'm sorry. Implies that this is our theta. Yep. So for friction, we would use cosine theta. Right. It's only part of the frictional force that contributes. Right. And then, but for the first part of the problem, we're assuming that this is 0. Right. And then in this case, we'll have this. Yeah. And then now we don't know Fn, we have to find Fn. Fn, if you remember from our inclined plane, is equal to the cosine of gravity, right? Remember Fn, you look back, equal mg cosine theta. I'm sorry, divided by cosine theta. Right? And then we plug it in over here. So we have mg is acceleration in the vertical direction 0.
Professor, somebody has a question in the chat.
So why is it divided? Oh, okay. So the forces in our vertical direction are this. Right, in our vertical direction, it's mg or cosine Fn. We're looking at the y component over here. Cosine Fn minus mg. And then A is 0. And then you really then you could just solve you could bring this over to the other side and you get this. And then finally you get that. Yeah. Okay. That's how I got Fn mg over cosine theta. So now I plug that into here, what I found, what I had earlier. Right? And then we solve. And then we find that tan theta is equal to the velocity over rg. And then when you plug it in, and then you get this. Right. And this gives you the angle for the banking angle, right? This formula gives you the banking angle for the radius of curvature and the speed. So it's very simple to calculate the angle, the banking angle, based on this. And you can design the roads properly so that you don't want any, you don't want that a car to use any static coefficient of friction, right? You want to set the proper speed, the speed limit to be at that particular angle for the bank. You want to make the bank of the road that particular angle for the speed of the traffic. Right? This gives more room for errors. You know, if the car is going faster, it has more static coefficient force due to static coefficient of friction to play with than you would normally have. Any questions on this? So that's about it. And then if we wanted to add in the coefficient of friction into this problem, right, the coefficient of friction in this case is just the normal vector Fn, right, times mu, and then we need to calculate the FFR, right, and that would just be cosine theta. And we just plug that in, we just add that into here, over here, which we have over here. All right. All right. Any questions? So that's it. So the test will be next week. I will give out the long answers. I will email you guys with the long answer part of the exam at the end of this week, either Thursday, Friday, and then it will be due the day before the exam, which would be on July 2nd. I will on September 30th. I have a meeting I have to attend. I'll try to do part of the time. We'll go over examples.
September?
What?
Did you just say September?
Oh, I meant July. Sorry. The reason why I said September was in our lab class. I put 9:30 on the instead of 6:30. So I was thinking of September. Anyway, it would be, the test would be July 2nd. We'll we'll do a partial review on the 30th, which is next Tuesday. And,
Is it going to be a study guide?
No.
I'll see what I can do. I'll let you know. But it would be up to chapter 7. I want to finish 7 by next week. So, and if not, I'll update it accordingly. And then the test itself on July will consist of 1 hour of short answers, and then we'll do an oral exam where each one of you will enter the room individually, and I'll ask you some questions and a long answer. Any questions?
All right, Professor. Enjoy your day.
You too. Take care, guys.
So the test is going to be 2 parts?
3 parts.
3 parts.
Two long answer questions that you get to do at home.
Mm-hmm.
Then there's going to be short answers done through Master in Physics, be akin to the quizzes, something like the quizzes, but longer. And you have to do it in the class. So actually, for the short answer problems, I need you to be in the room with your video on and your audio on, so I could hear you and see you working. Okay?
Yeah.
So I'll go over it again, but make sure that your video and your audio are working for next Thursday. So it consists of an hour of that, and then we'll go into private discussions for the rest of the time on Thursday. Okay?
Yeah. So 3 parts. Okay. Take
Yeah.
care, Professor.
You too. Take care, guys. Have a good day.